And we're looking at lesson 3.1, the chain rule. There's a little discovery example here, and it's not exactly clear to you why we're doing it at the beginning. Like, why would we review in this way? But let's try it, okay? So we know that if we have something that is squared, that means that itself times itself is what we're trying to do, right? That's how you expand it. And right here it says, let's actually take the derivative of that. So he says, Mr. Taylor, why don't we practice this with the product rule? So if I have x cubed minus 3 and I take the derivative of that, I get 3x squared. And if I have x cubed minus 3 and I take the derivative of that, I get 3x squared. And it'll be this piece times that piece and this times that piece, right? So my answer will end up being 3x squared times x squared minus 3. And it'll be another 3x squared times x squared minus 3. And I know you can tell that I'm basically adding up two of the same things, right? That this matches this. Not just that, though, that this matches this. So technically what I'm doing is I'm adding up two of these 3x squareds times x cubed minus 3. So there you go. Now, why would we want to review this in this way? Well, actually, it turns out when you use the chain rule, what you will notice is that if you think about it, if I just had something that was squared, I want to do this in red. If I had something that was squared and I took the derivative of it, wouldn't I end up with a 2 on the outside? And the power would be reduced down to 1. Then, even if I was just taking the derivative of x cubed minus 3, when I take the derivative of x cubed minus 3, that's how I get this piece here. So to generalize, what the chain rule is, I'm going to do this. I'm not going to make a separate freestyle here, but this is the freestyle moment where you take the derivative of whatever is on the outside. Okay? And that I usually put in front. I mean, typically. I write it down in front. Then I will take the derivative of the inside. So I did the outside before, now I want to do the inside, whatever function that is, and I will also put it in front, right next to the other one. And then 3, always remember the original function should still be in your answer. Okay, and this is freestyle for how to use the chain rule. Okay, take the derivative of the outside and put that in front. Take the derivative of the inside, put it right next to that. And always remember that the original inside should still be in your answer. Okay, it should always still be there, whatever it was. So having talked about those rules, this is what it looks like. Oh, what a beast. Maybe I'll change my mind about that freestyle one time. But basically what it's saying is that you are going to take the derivative of the whole darn thing, and that's what I call the outside. And you should take, oh, I should have written that in red. And you should also always remember to write the derivative of the inside. But I usually put it in front. He puts it in the back side. That's the way that he's memorizing the chain rule. I like to memorize it where you put the derivative in the front. And I'll watch me do it right now. Ready? I have the outside function, and it is something that is to the 4th power. So I'm going to bring the derivative out like this with a 4 out in front. And don't forget, remember what I said about don't forget? So when I had something that was to the fourth power, if I bring that 4 out in front, the power will be reduced down to a 3. And so since I happen to be writing it right now, why don't I go ahead and write down 3x cubed minus 5x. That's actually the last step where I say, don't forget that whatever was on the inside, you should still have that as part of your answer, right? So I had that 3x cubed minus 5x. It was to the fourth power. I brought the 4 out in front. I reduced the power down to a cubed. And whatever was in there, it should still be in there. But what else? Well, I should also take the derivative of that inside. And the way that looks is it looks like this. 3x cubed is 9x squared, right? Because I took the derivative of 3x cubed. Take the derivative of negative 5x and I get a negative 5. And that's my answer. And that's it. That's all I do. Now, if you want to see me write it with like more steps, you're like, oh, that happened fast. I'm not sure what happened. Well, right here, I took the derivative of the inside and I wrote it down, and I'm calling that step 2. Here, I took the thing that was on the outside, and I wrote it down, and I call that step 1. And then here, whatever is on the inside, whatever that is, it should still be present in your answer, and I say that that's step 3. Now, whether or not I actually hold to doing step 1, 2, and 3 in order, you know me, I have a hard time keeping things in order. So I just do it when it occurs to me. But those are the 3 steps, okay? If I was going to show you how to do it with more work, like showing you, I guess, 2 steps, here's what I would say. For number 2, if I want to find y prime, I know I'm supposed to take the derivative of the outside function. The outside function is sine. So cosine will be in my answer. And remember what I said about that inside? The inside should still be there. So I'm actually doing step 3 first. I apologize. That's just the way my brain works. The second step says we take the derivative of the inside. This is how I write that. d dx of 3x means, please don't forget to take the derivative of the inside. This is the chain rule. This is where I'm using the chain rule, okay? Now, I know that Mr. Taylor sometimes calls it the hook-on, and he says his students really like it when he calls it that. I have a hard time remembering to say that out loud, but I've been practicing, so maybe I'll try it. Don't forget your hook-on. The hook-on is the derivative of that inside function. And by the way, what is the derivative of 3x? It's 3. So my final derivative when I'm all done will be having a 3 in front of it plus times cosine of 3x. Okay? There you go. Now, what about number 3 then? Well, let's take a look at number 3. There's a lot going on there. It feels like there's an outside function, which is a square root. It feels like there's an inside function, which is a cubed. And then it feels like there's another inside function, which is 2x squared minus x. And so I want to say, I think that it actually might be better if I convert this over into that rational notation, right? Where g of x is really what function? G of x is really 2x squared minus x, and instead of to the third power, it's to the 3/2 power. Now, what are you doing, Ms. Shatra? How are you allowed to do that? Well, remember, if I had something that looks like this, where, I think I usually use the n on the outside, sorry. So if I have x to the power of n, and then I want to take, sorry, I said n, x to the power of m, and I want to take the nth root of that, then it should be x to the m over n. So the reason that I'm able to do this is that there's a hidden invisible 2 there, and it doesn't matter, by the way, some kids get confused when they see that m on the inside or if they see the m on the outside. It doesn't matter where it is, if it's inside or outside of that square root. I know eventually that I'm cubing something. So here's me cubing something and here's me rooting something. So I'm allowed to do this, okay? Now for g of x then, I have defined it in such a way that I really only see 2 functions now. I see the 3/2, and I want that to come out in front. Remember what we said about powers. Bring it down, out in front. That's step 1. Don't forget to write that power being reduced by 1. So I have 3/2, which is 1.5, which if I take away 1, I should have a half left. And that the inside, whatever was in the inside, should still be on the inside. 2x squared minus x. I'm not changing the original function in terms of it. It's still part of my derivative, okay? Just like when you take the derivative of x squared, you still have an x when you're done, right? You have a 2x, which means you still technically have that inside function. All right, so anyway, that might be worth saying something about. If I have x and it is squared, if I use the chain rule says take that 2, put it out in front, and you still have that inside function. And don't forget to reduce the power by 1. So the chain rule works with the power rule, just the simple power rule. So I just thought it might be worth actually, saying. Sometimes I might have cut something like that, but I'm going to leave it in here for now because I think it's helpful. Now, the last thing was I've done step 1 and I've done step 3. I haven't done step 2. So I know you guys hate me for this, but here you go. Now I'm going to do step 2, and I don't even know what color I'm supposed to be using right here. The derivative of 2x squared is 4x, and the derivative of negative x is 1. And so, ta-da, that is my final answer. I'm not going to do anything else to it. I know that's really just a plain old square root now, but I don't care. I can leave it as a rational exponent. And now I get to move on. So for number 4, then, h of theta is equal to 3 cosine squared of theta. And, what's my outside? What's my inside? So I'll mention that oftentimes students, they really do not have a handle on that squared. The fact that it shows up at all really messes with your brain. It turns out that cosine of theta is what is being squared. So that is what h of theta really is. It has an inside function now, and it has an outside function. The outside function is a 2. So if I want to find the derivative of this, h prime of theta will end up being 3 times 2, because, right, there was a 3 in front, and now the 2 is coming down and out in front. And don't forget that you have that inside function. The inside function is cosine of theta. And then I did step 1, I did step 3, I forgot to do step 2. Here is step 2, and I'm sorry about this, you guys. Step 2, take the derivative of the inside. The inside is sine of theta. Ta-da! So that will be my final answer. Okay? Now, for step 5, we have g of x equals 1 over 2x plus 1. And I have 2 different ways that I could do this. I could do this using the quotient rule. And for practice, it might be a good idea that you practice that. But I wanted to point out to you that the chain rule exists, and it's useful now. It's extremely useful now. So if you wanted to, you could change g of x and write it in this way. G of x is really equal to 2x plus 1 to the negative 1 power. And why am I allowed to do that? Because everything is always to a power, even hidden invisible power of 1. If it's in the denominator, I can bring it up into the numerator and just make it negative. So now, if I want to use the chain rule, I say that g prime of x equals, that power comes out in front, and then it gets reduced by 1. So if I have a negative 1 and I take away another 1, I end up with a negative 2 here. And don't forget that original function, 2x plus 1, it's still supposed to appear in your answer. And then as the last piece right here, I guess this is where I should have been in green. Now I wish I'd done everything. That original piece should be in black. Okay, so the derivative of the inside, step 2, that's what I haven't done yet. The derivative of the inside is the 2x plus 1. The derivative of that is just a 2. So that's my answer, but I have kids in my class. I know you all so well. It bothers you that I leave it like that. So I'm going to write it like this. Ready? Negative 2 over 2x plus 1 quantity negative. positive too, because I'm bringing it down into the denominator and I'm making it positive. By the way, this should jibe with your recollection of how to do the quotient rule. Yes, the quotient rule says take the denominator, square that sucker. And so I did. But how you end up with a -2 on top, yeah, you would end up having to do a lot of algebra to get that. When we use a chain rule, we can kind of skip all that algebra and end up in the same place. It's really quite nice. So I recommend this method if you can remember that it's a possibility. You know what I mean? So for number 6, then, I see that what I have here is two functions that are being multiplied together, but it's a little bit hard to tell what they are. So let me see if I can redefine f of x in the following way. 3x squared, ta-da, is one function. The other function is 9 minus 4x squared, and that quantity should be taken to the 1/3 power. Right? My root is 3. And there always was a hidden invisible 1 right here. You just didn't know it, right? You just didn't remember that it was there. So now I know that I have this thing's time that thing. When I want to do the derivative, I take the derivative of 3x squared. 3x squared, and I will get a 6x. Ooh, when I take the derivative of this nasty beast, 9 minus 4x squared, and have that be the 1/3 power, well, I need to use the chain rule because I have an outside function, which is that 1/3, and I need to reduce that power by a whole. So I have a third and I take away a whole. That leaves me with -2/3. Oh, handwriting, terrible. Let me fix that. 2/3. And then inside, you should still have that regular old function. Don't get rid of that original interior function. But when I am taking the derivative of it, remember, I do take the derivative of the inside, and what do I end up with? Well, the derivative of 9 minus 4x squared is a -8x. Ta-da! That's pretty ugly. Let's see if I can't clean it up a bit before I start writing it down. You know what I mean? I would say then that what I have is, you know what? I don't even want to clean this up. -8x over 3 times 9 minus 4x squared. I'm just going to leave it with a -2/3 power. Okay, so it'll be this times this and this times this as the answer to what is f prime of x. Ready? F prime of x is 3x squared times -8x over 3 times 9 minus 4x squared to the -2/3 power. And when I say and, I do mean plus, and a 6x times the 9 minus 4x squared to the 1/3 power. Ooh, that's a nasty looking derivative. Yeah, I didn't say, that derivatives were easy. Turns out I could have written this like on a couple of lines, right? The more you write, the smarter you feel. That's what I'd love to think. Okay. Last one of this style where I'm just trying to take the derivative using the chain rule. Ooh, what's my inside function? What's my outside function? Okay, here's another one of those moments where I really feel like I have like several functions, not just 1, 2, 3 different functions, right? I have that inside function, which is 4t squared, but technically I have 2 inside functions because I have this sine of something. And then the third function really is that thing is cubed. So if I'm trying to make my life just a little bit easier, f of t is going to be sine of 4t squared, and I put that cubed on the outside to remind me, where's my first step? My first step, ready, is f prime of t is going to end up being that 3 comes out and is in front, and then sine of 4t squared should now be squared, right? So the original function appears in your answer unchanged, except for its power has gone down by 1. And then I need to take the derivative of sine of 4t squared. So that'll be a cosine of 4t squared. But guess what? There was another function on the inside, and that last function that's on the inside, the derivative of it, the derivative of 4t squared, is 8t. And that is one heck of an answer. Whew. To take the derivative using the chain rule, when you get to that third time that you're trying to do a derivative, it can really hurt your brain. So this one, you just need to practice it a few times. The more you practice it, the better you'll get at it. So now we're moving on to number 8, and when I'm looking at it, it's going to give me a table of values. We practiced this a little bit in class recently, so hopefully you'll find, oh, hey, let's take a look at part A. All this is the product rule, right? The product rule says if you want to take the derivative, you should take the original function and take its derivative and multiply it by the other original function. If you want to continue with that product rule, you would take the derivative of the one you haven't taken the derivative of yet, and then multiply it by the one that you hadn't done yet. So there you go. And by the way, if I want to do f prime of 2 for this, then I would say find what p prime of 2 is and multiply that by q of 2. Find what q prime of 2 is and multiply that by p of 2. And the numbers that I get here, I've run out of room, but I'm sure you can follow. The numbers I'll get here, p prime of 2 will be this guy, right? P prime of 2 will be this guy, so I'm going to get a 7. And q of 2 will be that guy, so there will be a 3. And then q prime of 2 is that 6, and p of 2 would be that 5. And I end up using every number in this table. 7 times 3 is 21, and 6 times 5 is 30, so I end up with 51 as an answer. Okay, if I'm going to do number 8, part B. Okay, look, if I'm going to do number 8, part B, I'm actually going to end up using, what is this right here? The chain rule. I have it memorized. You have copied it 3 times. I'm just not sure which version you may have copied. So I know a lot of kids prefer the version that I'm about to write down, which is that if you're taking the derivative of a function that is composed with another function, that it should look like this. The derivative of the outside should be taken, and the inside still gets written down. And you should never forget that hook on, which is the derivative of that inside function. And in the lecture notes so far, I've been talking about this outside function. We take the derivative of it first in red, and then like if it was a power, I would reduce that power by 1, and I would say, oh yeah, I'm doing step 3 here, where I always write down that original inside function, and then I say, but don't forget, step 2 is to actually take the derivative of that, and I usually write it in front. So if you have this version of the chain rule memorized, this is actually pretty sweet for you, because it turns out if you look very carefully at my letters and my colors here, this is my outside function and this is my inside function, and it looks a lot like, you know, this. So I'm thinking, actually, I wish I had thought to line these up better. I bet that what I have going on here is a straight swap from F's to P's. And I plan to write this rule, instead of using an F, I will write a P. And here, instead of writing a G, I will write Q's. Okay? And then I'm going to figure out what to do about that too. So I know that that might not have occurred to you before, But I have mentioned when you go out on the internet, you see, I've told you, I want to show you multiple versions of the chain rule. I want to show you multiple ways of writing down the product rule, the quotient rule, whatever. I gave you all these options for which one you memorize, so that if you do go out on the internet, you'll see, oh, unrecognized. Yeah, that's still the chain rule. They're just using different letters, okay? So I want to say then that if I'm doing this straight swap from F's to P's and from G's to Q's, that I can now take the derivative in the following way. This F turns into a P, this G turns into a Q, and there's my X's, and there's my prime mark, and that G turns into a Q, and don't forget that prime mark, and there we go. Straight swap. I changed that F to a P, I changed that F to a P, I changed this G into a Q, I changed this into a Q, I changed this into a Q. Kind of funny, if I didn't want to even bother with all of that work, I literally could have done this instead. I could have changed this P into an F, I could have changed that into a G, I could have changed that into an F prime, and I could have changed that into a G prime, and still completed the work in the same exact way. Okay, so this question does appear on the AP exam. It's like a multiple choice style question. They do want to test you that you know what the chain rule is, and so that's why I ask you to memorize it. That's why I want you to have it copied 5 times. Now, what if you didn't choose this version? Don't worry, it's a conceptual piece. You will still, with the version of the chain rule that you memorized, you will still be able to do it. And I'll be demoing that in class, all right, directly in class. Not in this video right now, but you'll see it. So if I want to find h prime of 2, first of all, let me connect one last piece, which is that h of x is this composition. So what I said is now the derivative of h prime of x, right? Take the derivative of h of x, then I will end up with this derivative right here. Sorry, let me get rid of that right there. So this derivative will be that right there, okay? And now I can start plugging in numbers. So I say h prime of 2 is going to be p prime of q of 2, and that ends up being q prime of 2. Ta-da! And then I will say that I should figure out what q of 2 is. And maybe q prime of 2, because that seems pretty easy. Here's the 2, and here is q of 2 is a 3, and q prime of 2 is a 6. And I don't have enough colors to highlight these, so I'm just writing them down. Okay, so then I should bring down what's the rest of the problem. There's a p prime left here that I still haven't evaluated, but q prime of 2, I evaluated that, and I found out that it was 6. So what is p prime of 3? Well, here, let me break out another color now. There's something of 3, and here is where the p prime of 3 lives. So p prime of 3, all of this, when I evaluate it, I get an 8, and there was a 6 already there. So my final answer will be 8 times 6, which is 48. Whew, that one's a toughie. Let's hope that Khan Academy has some practice of this.